What's up guys, welcome back. Today we're going to be building the first part in a 2 video series on how to make an audio visualizer in Roblox, a very simple audio visualizer. But today we're just going to be making a ball that's going to get bigger and smaller depending on the sound, the volume of a sound. So we can start by inserting our music. So I have this here, I'm going to insert that into the sound service. We go ahead and make sure. So that's the sound I'm going to be using. I'm going to turn the volume down, and I'm going to click on this playing button right here to make sure that plays when our game starts. Now we can go ahead and put a local script inside starter player scripts and rename it to something like sphere visualizer. Now the reason we use a local script is so we don't put too much strain on the server, right? Because we're going to be doing a lot of animation here. We're going to be running code every frame. So it's better to put that strain on the client than the server. And the reason we put it in player scripts is because if we put it in starter character scripts, when the character died, it would actually reset the script, right? Because we're creating a new character, putting the script inside the new character. But if we put inside starter player scripts, right, it'll stay inside the player the entire time. Okay, so we could start by making a ball. Oops, and set that equal to instance.new part. And we can make that part a ball. So enum.partType.ball. And now the next thing we can do is we can raise this ball a little bit in the air. So 15 studs off the ground. Now the next thing we can do is we can anchor the ball, right? So we can prevent it from moving. And then we can make it non-collidable. Oops. So that when it expands and contracts, it doesn't push things around or bump into things. Now the last thing we can do is we can set the ball's parent to workspace. And we go ahead and run our game, and we can see there should be a ball in the workspace. Just turn this off. Now you can already see there's studs on the top and inlets on the bottom, which is actually taking away from the smoothness of this ball. So if I go down here, you can see on the bottom surface, we have inlets, top surface, studs, and all the other surfaces are smooth. Right, so if I go ahead and change these two to smooth, you can see this is what we want the ball to look like. But unfortunately, it doesn't look like that. It doesn't look like that right now, because when you spawn a default part, for some reason Roblox decides to put studs on the top, inlets on the bottom. I have no idea why, but we can fix that. All right, if we go into our script, we can say ball.topSurface equals enum.surfaceType.smooth. Right, we can set the top surface to a smooth surface. And we can do the same thing for the bottom surface, enum.surfaceType.smooth. Now if we run our game, we see that it's smooth. The next thing we need to do is we need to get a reference to our music in our script. So you can do this in a number of ways, but I'm actually going to insert an object value under our script. I'm actually going to call this music, and I'm going to click on value, and I'm going to click here. Then in our script, I'm going to say local music value equals script, wait for child, music. And this is going to give us this value here. Now once we have this value here, we can actually use this to get the actual music. We're going to do that in a second. Now, let's go ahead and make a function to update our visualizer. We're going to put D in here. I'll explain that later. Actually, let's call that DT. I'll explain what that does later. What we can do is we can say ball.size is equal to vector3.new music value.value. So we're going to this value here, getting the value, which is equal to this, right? You click on this, and you can select your music here. Dot playback loudness. Now what playback loudness is it basically tells you, right, how loud the sound is at a given point in time. So if the sound is really loud, this value is going to be really high. If the sound is really quiet, the value is going to be really low. And this allows us to create this sort of audio visualizer effect where you have the ball that expands when it gets louder and contracts when it gets smaller. Now, let's copy this and paste it 2 more times so we have 3 values. And the next thing we want to do is actually run this code every frame, right? Because we want it to look smooth. So let's go ahead and get the run service. get service, run service. And then we can go ahead and connect this function to the heartbeat event. Now, heartbeat is an event that is called or fired every single frame. Okay, so now that we've connected our function to the heartbeat event and it's running every frame, let's go ahead and see how this works. So you can see that it's a bit large, but the general idea is there, right? As the sound gets louder, the ball gets bigger. As the sound gets quieter, it gets smaller. Now we can obviously make this a bit smaller by, I'm going to make a variable called L. I'm going to set that equal to this. Right, we had that before. I'm going to multiply that by some value, so 0.04. That's sort of going to tone down this value. And I'm going to replace all these values here with L. So I'm going to put L here and L for the other two values. Now if we run it, we should see that it's a bit slower, or a bit smaller. Notice how it's not very smooth, right? It updates to the sound instantly. Watch how it sort of snaps. Right, we want this to look smooth. So to do that, we can use the lerp function. Right, so we can go ahead and put our lerp function here. We can say ball.size, lerp to vector3.new, LLL, and then we put one new value after here. Now this value is in a range from 0 to 1. So I'm just going to put 0.1 for now. I'll explain exactly what this does in a second, but for now let's just go and see the difference it makes. Right, so the ball's a lot smoother, right, than it was before. It's not like teleporting to the position, it's moving smoothly. But what exactly is the lerp function? Let me go over to Paint and explain that. Okay, so here I am in Paint. Now what we've essentially done is we've said that let's define a couple of values. So let's say A is equal to our starting position. Well, I can actually just write this. So A is equal to our starting position. And let's say B is equal to our ending position. Right? And let's give one more value. Let's call D our alpha value. So now we have three values, right? And we can write this out in a lerp function. Lerp A, B, D. Now lerp stands for linear interpolation. So we're basically picking a point on the line between our two positions, right? And this point is going to be a percentage of the distance between the 2 points. And that distance is represented by D, or that percentage of the distance is represented by D. D is going to be a value from 0 to 1. And that basically tells us how much of the distance we're going to go. So if D was 0, we'd go none of the distance. We'd stay at point A. If it was 1, we'd go the entire distance, and we'd end up at point B. What we're doing is we're saying A is equal to lerp A, B, D. And this is basically moving the starting point every single time we do it. And we could sort of see when you do this, we won't actually ever reach the destination. Because, say D was, let's say, 0.5, right? And that equals 50%. So we're going 50% of the remaining distance every time, right? Of the remaining distance, right? Not of the actual total distance, because A changes every time. Say I had 2 points. Let me draw this out really quick. So this is a point here, and this is a point here. And then this color will represent the total distance we need to travel. Now, when I first start, we'll end up here. We'll go halfway, right? So this was A before, but now we've just set A to be lerp A, B, D. So A is now this, and now we're going to go 50% of the distance between A and B. B stays the same. So we end up here. And now this becomes A. And then we end up here. And this becomes A. And then here, A, and then here. But you can see we never actually get to B. It'll just keep getting cut in half, and then in half, and then in half, and then in half. So we'll never actually reach our destination, because we're going a percentage of the remaining distance every time. Now, this sort of creates a smooth effect, because the rate of change starts to go down over time. It's big here, and it's smaller here. As you can see, it keeps getting smaller and smaller over time. So that's what creates the smoothing effect we can create with lerp. So we go back to our code, and we can see that working here. Have a look at the smoothing effect we can see on the ball. Now if we set this to 1, right, watch what happens. It's the same as before, as if no lerp. And this is because, 1, you're going the entire distance every time. So we skip all of this. This doesn't matter if a equals 1 or if d equals 1. Because we're not going 50%, we're going 100%. So it doesn't matter what comes after. We're already there. But what exactly is lerp, right? How does lerp work? Why is it doing this? Let me show you what lerp is. So lerp is equal to, in this situation with the values we have here, this is actually giving us a plus b minus a times d. And if you look at this, this actually makes sense, right? Because we take our starting position, we're adding the ending position minus the starting position. That's giving us the total distance we need to travel. And then we're multiplying the total distance we need to travel by some value to shrink it. And when we add that shrunk value, we go a percentage of the distance. So if d is 0.5, we're multiplying the distance we need to travel by 0.5, right? We're dividing it by 2. We're getting 50% of it. We're adding 50% of the needed distance to a, and we're going 50% of the way. So now that we understand lerp, there's one more thing I want to point out, right? And this is where things sort of start to get complicated. Watch what happens when I run this. Oops, let me go ahead and just set this back to what it was. 0.1. 0.1 is our alpha. Take note of how this looks right now. Now I'm going to go ahead and change my frame rate. I'm going to go to 240 FPS. Watch how much, look how much faster that is. Now I'm going to go down to 30 FPS. Now I'm going to go to 240 again. Now back to 30. Notice the massive difference between the frame rates. But why exactly is this happening? Let's go back to our code. We know that this code is running every single frame. And we know that this is saying we're going to go 10% of the remaining distance every frame. So that means that someone with 30 FPS is going to go 10% of the remaining distance 30 times in a single second. Someone with 240 FPS is going to go 10% of the remaining distance 240 times in a single second. So one of them is going to be able to move a lot more in that 1 second time period than the other. So how do we sort of balance these two? How do we fix this? What do I put as an alpha value to balance this out? Well, that's where this value comes in, dt. Now, dt is short for delta time. And delta time represents the time in seconds between the frames. And that can be represented as 1 divided by the frames per second. If I have 10 frames per second, I do 1 over 10, I get 0.1. There's 0.1 seconds in between each frame when I have 10 FPS. And that makes sense. If I add 0.1 10 times, I get 1, and that's equal to 1 second. So now, how do I use this though? How do I use this value to balance out the frame rates? Well, I could put it here, right? I could put dt here. And if you were to run this and go through this, you could see that it actually would look pretty similar between the frame rates. I could switch between the frame rates, and I wouldn't really notice a difference. However, if I wanted to actually change this, right? I wanted to make this value larger because if I thought it was too slow or something like that, you might try multiplying this by a certain value, say like 50 or something. Now this is where things get complicated, because say dt is a very low value because you have a very high FPS. This would work. This would be fine. If you have a very low FPS, which means delta time is really high, you actually have the possibility of delta time multiplying by this number and ending up being more than 1. And that leads to overshoot, because you can't go more than 100% of the distance between 2 points. That means you go past it, and then you'll come back, and you'll sort of do this spring motion, back and forth, back and forth, back and forth, and you'll never actually get to where you want to be. You'll just keep going past where you want to be. So, what is the solution to this? A, this isn't accurate. They look similar, but it's not completely accurate. And B, we have the possibility of overshoot. It's going past. So what do I put here? What can I put as D? So I can actually write 1 minus a value, we can call that F for now, to the power of our delta time. And we can put that in our lerp function. So say we wrote lerp A, B, and then this. F represents the remaining distance after 1 second. So if F was 1, the remaining distance after 1 second would be 1 or 100%. Everything would still be there. I wouldn't have traveled anything. If F was 0, there would be nothing left after 1 second. I would have traveled the entire distance. So, why does this work? Well, to understand why this works, we have to understand how we figure out how much is left after a certain amount of frames. So let's go with a situation like lerp, point A, point B, 0.1. I'm going 10% of the distance every frame. Now in a situation like this, we can see that after a single frame, we would have gone 10% of the distance. This means we have 90% of the distance left, because 1 minus 0.1 equals 0.9. We have 0.9 left after 1 frame. Now we know that because A moves, after we set A equal to lerp A, B, D, we know that we're taking 90% of the remaining distance every frame. So this means on the next frame, we're going to be taking 90% of that 90%. On the next frame, 90% of the 90% of the 90%, and etc. So to do that, we can actually represent this as 0.9 to the power of n, n representing the number of frames. Now, this is where things start to make a little bit more sense. With this over here, to figure out how much is left after 1 frame, we just simply take this. So f to the power of dt is left after a single frame. And that means after n frames, like over here, to figure out how much is left, we can simply raise that to the power of n. Now this is where things start to get interesting, because we know that dt is the time between frames. And there's a special relationship between the number of frames and the time between them. dt can actually be represented as 1 over the number of frames. So now we can substitute that. So we can actually represent this as f to the power of 1 over n to the power of n. And now what we know about exponents, we know that we can multiply these two, and it will be the same as it was before. And what is 1 over n times n over 1? That leaves us with n over n, or just 1. So that means what we're really doing here is raising f to the power of 1, and that's just equal to f. So that means that f is equal to f to the power of delta time to the power of n. So that means that after 1 second, we have f left remaining, because this is equal to this. So now, taking that knowledge, let's go back to our game. We can put here 1 minus our f value, which let's just say is 0.1. We want 10% of the distance to be left after 1 second. And we can raise that to the power of delta time. And now if we run this, first of all, we retain the same smoothness as before. And let's mess with the frame rates. I'm at 60 right now. I'm going to go to 240. I'm going to go back to 60. I'm going to go to 30. I'm going to go to 60. I'm going to go to 30. I'm going to go to 240. They all look the same. So that's it. That's all we have to do. 1 minus f to the power of delta time. So that's it for this video. Thank you guys for watching. I'll see you in the next one. Don't forget to like and subscribe. It really helps a lot. But yeah, I'll see you guys in the next one.